In this lesson, we're going to develop the law of cosines using triangle ABC. I'm going to put vertex C at the origin. I'm going to put vertex B somewhere on the x-axis. I can make it any distance I want. I'm going to put vertex A out in the plane, and I can move that anywhere I want. The main focus is that if I make A, vertex A out in space, then segment A, which is across from it, will be the length from B to C. Once I know that I have the length of A, I also then have the coordinates for B, which would then be A comma 0. To get the coordinates for A, I have to go back and look at my unit circle and realize that if I have angle C here, I know that the coordinates where B crosses the unit circle would be cosine C, sine C. But that is for a radius of 1. Think of this as a big circle of radius B. If I held out that far away, then it would only be expected that my coordinates for A will be B cosine C, B sine C. Why is that important? Well, our goal here is to find the distance between A and B, which means we're going to try to find the value of C. To do that, I can go back to the distance formula, which is D equals x2 minus x1 quantity squared, that's an x2 minus x1 quantity squared, plus y2 minus y1 quantity squared. Except my distance isn't going to be D, it's going to be C. So I'm going to put in C here. And I actually have my two coordinates. My x2 could be B cosine C. And my x1, yes, we'll call this x1 and we'll call this x2. My x1 would be A. And I could square that. I could also then say this is my y2, which is B sine C, and I could subtract my y1, which is 0, down here and square it. So by definition, that would be a way to find the formula, but I think we can clean it up a little bit. And to do that, the first thing I think I will do is square both sides. So we'll get rid of the radical, and we're left with B cosine C minus A quantity squared. And technically, since it's just B sine C minus 0, we can get rid of the minus 0 and just say it's B sine C quantity squared. Well, I'm going to expand the binomial, and I'm going to work out B cosine C minus A, and I would be given B squared cosine squared C. Remember, it's cosine that's squared, not the C. I would have 2 AB cosine C because of foiling. I would also have a plus A squared. And then finally, I would have a plus B squared because the B would be squared and the sine would be squared. And I would have a formula now for C squared. I don't think this would be a friendly formula to work with, so let's see what I can do. And I think the first thing I'm going to do is I'm going to write A squared first. I'm going to put B squared cosine squared C, add that to B squared sine squared C, and at the end I'm going to subtract minus 2AB cosine of C. The reason I'm going to do that is because if I factor out a B squared from cosine squared C plus sine squared C, leaving A squared and minus 2AB cosine C alone, the advantage is, and I'm going to put this in blue now, is that this is Pythagorean's identity. And Pythagorean's identity says that if you take a cosine squared of an angle plus sine squared of an angle, this ends up equaling a big giant 1. And so if I go back to my formula, I can actually say that c squared equals my original a squared. I will add b squared times 1, which is b squared. I'd be left then with minus 2ab cosine of c, and congratulations, we have just developed what is called the law of cosines. If you look at this really carefully, this should be very familiar. In fact, it only takes a little bit more memorization of Pythagorean's theorem. There's Pythagorean again. It only takes a little bit more memory of this. You could say c squared equals a squared plus b squared for right triangles. Oops, don't know how to spell the word right. Right triangles. Well, this formula, the law of cosines, can be used for any triangle. And because it can be used for any triangle, the only difference here is you just have to remember one more piece. Just add on the minus 2ab cosine of c. Thanks to the power of editing, I've gone ahead and created a 3, 4, 5 right triangle. I'm going to label them B is 3, and A is 4, and C is 5. More specifically, it's a 90-degree right angle. And what I want to focus on is how close, or how Pythagorean's theorem and the law of cosines go together. And to best demonstrate that, let's go write out the law of cosines. C squared equals a squared plus b squared minus 2ab cosine of c. Now, it really not worrying about the fact that I've made it a 3, 4, 5 right triangle. The big deal is I've made it a right triangle. So it doesn't matter if it's a 5, 12, 13, or let's see, if it was 4 and 5, that would be 16 plus 25, 41, so square root of 41. The key is I'm making angle C a 90-degree angle. So what I'm going to do is I'm going to plug 90 degrees into the cosine of C. So c squared equals a squared plus b squared minus 2ab cosine of 90 degrees. If I were to go to a unit circle and I was at 90 degrees, this coordinate right here would be 0, 1. And since my x-coordinate happens to be the cosine of 90 degrees, I could then substitute c squared to equal a squared plus b squared minus 2ab times 0. That's my cosine of 90. Realize that anything times 0 is, well, 0 for this whole piece. And so therefore, for all right triangles, we would get c squared equaling to a squared plus b squared. And so you can see how the law of cosines, which is the all-purpose formula, can also be used for right triangles, because essentially we just eliminate the one piece right here. And that is the overview of the law of cosines. In another video, we'll show you how you want to actually apply the law of cosines to different types of triangles.